Welcome to Summarize Science. Today, we're looking at a fascinating paper that tackles a huge headache in the world of artificial intelligence, training instability. You see, when developers fine-tune large language models, the process can be notoriously shaky, sometimes even collapsing entirely. For a long time, experts have pointed to a problem called the training-inference mismatch. Think of it like this. The AI uses one method to learn during training and a slightly different, faster method when it's actually working or inferring. Even though these methods are supposed to be mathematically identical, tiny differences in their calculations can build up and cause major problems. Previous attempts to fix this involved complicated software patches that were expensive and didn't completely solve the issue. But this paper suggests the root cause isn't in the complex algorithms, but in something much more fundamental: floating point precision. Most modern AI training uses a format called BF16, which is great because it can handle a huge range of numbers without errors. However, it sacrifices precision to do so, meaning it's not very good at telling the difference between two very similar numbers. The researchers had a simple idea. What if they switched back to an older format, FP16? FP16 can't handle as wide a range of numbers, but it's much more precise. It's like using a ruler with millimeter markings instead of just centimeters. The results of this one simple change were absolutely dramatic. In graph after graph, you can see the performance of models trained with the old method, BF16, shown in blue. Many of them start to improve, but then they become unstable and their performance collapses. Now look at the green lines, which represent the models trained with the more precise FP16. They are uniformly more stable, learn faster, and achieve a much higher level of performance without collapsing. The researchers found that this higher precision in FP16 virtually eliminates the mismatch between the training and inference processes. The tiny rounding errors that plagued the BF16 format simply don't accumulate as much, keeping the whole system in sync. This makes the entire training process smoother and more reliable. Even when comparing FP16 to the more complex algorithmic fixes, the simple precision switch came out on top. It outperformed all the other methods that were specifically designed to solve this exact problem. This suggests everyone might have been looking for a complex solution when a simple, fundamental one was there all along. So let's recap the key points. The instability that frustrates AI developers is largely caused by the low precision of the standard BF16 number format. Simply switching to the higher precision FP16 format solves this problem at its core. This one change leads to more stable training, faster learning, and, ultimately, better performing AI models. What does this mean for the future? It could make developing powerful AI much more efficient and reliable, saving immense amounts of time and computational resources. It's a powerful reminder that sometimes the most elegant solution to a complex problem is the simplest one. Thanks for joining us on Summarize Science.